So a CQM is a constrained quadratic model.
And what that model does is it allows us to express a problem as an objective in a series of constraints.
What that means is we have constraints, so things that you must observe, and then you also have to express your question using only linear or quadratic terms.
So the first thing we had to do was understand our chemistry. What values were we trying to optimize for? And then we set those as our objectives. So we wanted to make sure if we were trying to minimize or maximize a value, that was the objective. And then what we did is try to represent what constraints limit that objective. Maybe only certain molecules could play with each other. Maybe the entire system had to stay under a certain range. So once we got those objectives in place, we could put those all into the CQM, send those to the quantum computer, and we'd get that results back.
The beauty is trying to frame your question in those terms, something that you can actually solve on the QPU. How do you take, a question about the world and frame it in terms of math?
Yeah, I'm really excited about this little tutorial that we've been putting together. It's actually, we've taken trying to optimize a chicken and waffles menu for the most pleasant dining experience. So what we've done is enumerated essentially all the waffles, all the different types of chicken you could get, the different sauces you could get, and put constraints around it like, yes, you must choose one from each category. The calories have to be less than a certain amount, but then our objective is the lowest price. We have that problem both described but also running in a Git repo. So you could go to the POLARISqb website, go find the link to our GitHub, and then clone this repo and try it for yourself. All you've got to do is grab the D-Wave key where we show you how to achieve that, and you too can be solving optimization problems with the D-Wave quantum annealer. Well, we've been working with D-Wave for about 2 years now, and what we've noticed even internally is that now that we understand that we have to have an objective and then that series of constraints, that we have multiple problems that actually fit that model. So we have problems that may take an entire system, hey, what do those constraints look like? But we have other problems that say, hey, how well do these molecules play, or what type of connections look like? So we've already understood that as long as we get that objective, and then we take the piece by piece for constraints, we can achieve optimal answers back from the quantum computer. Now that we think about that, there are quite a few problems that we can represent as that objective and constraints. So I'm really excited to see where the possibility goes for this type of technology.